Hello, you absolute legends. I got a question about how we describe electrons as either localized or delocalized. So when we describe electrons that are in an atom, this is just meant to be the nucleus of any atom, and this is just meant to be some of, like, say, the one shell or the two shell of the atom. We would say these electrons are localized on that atom. If we talk about electrons in a bond, these are the nuclei, and here are the electrons in, say, the 1s or 2s that are being shared as part of a bond. Now, in both of these instances, we would say the electrons are localized. You're not going to hear the term localized electron when talking about a single atom. When talking about a single atom in chemistry class, it's usually before the discussion of bonding. We usually don't use that term too much, but you could say that the electrons are localized on a single atom. When we talk about bonding and we're talking about multiple bonds or larger, more complicated items, whether electrons are localized or delocalized comes into some phrasing. I want to draw some pictures and kind of discuss what we're talking about. So just like a simple molecule, the simplest molecule there is, arguably, is the hydrogen molecule. We have a localized bond. It has to be a localized bond because there's nothing else that is going to happen there. It is a sigma bond that's occurring right there. Another simple common molecule. And again, these structures, these are derived from the Lewis dot structures right here. Here we have two localized bonds. Now, these sigma bonds are the first bonds formed. They're the strongest bond. We say that this bond is localized between these two atoms right here. Now, when atoms get a little more complicated and they become larger, we have this, and they still need to require and fill their octets. We have, this is the carbonate anion. So in this carbonate anion, we have localized sigma bonds that are going to stay, these two electrons are going to stay in between those two atoms. So they are localized sigma bonds, localized electrons. Now this pi bond here can become delocalized. Now, a way to imagine these delocalized pi electrons is that they are hopscotching around, and it's very difficult to play tag with them. So for example, electrons in this bond here, they're not going to stay in between these atoms or on these atoms. And we can draw structures. I'm going to leave off the lone pairs of electrons for the sake of lone pair electrons are also localized electrons on the atom, but for the sake of this discussion here. Now, just a simple way, but not like, absolutely correct, thinking about these pi electrons, these electrons being hopscotched around. So we see between all three of these structures, the three sigma bonds are there, they're localized. There are electrons in a pi bond, and we say they are delocalized because they're kind of smearing across the molecule. Another example of delocalized electrons in resonance, which is another buzzword to describe some of this stuff here. The resonance of delocalized electrons is the molecule benzene, C6H6. This hexagon right here is benzene. Note we have a lot of pi bonds. Well, I'm sorry. Note we have a lot of pi bonds and a lot of sigma bonds. We have, uno, dos, tres, we have 12 sigma bonds in this molecule, and we have pi bonds. Now, in that carbonate example, the pi electrons can become delocalized because whether it's a carbon bound to one oxygen or it's the carbon bound to the other oxygen, the electrons didn't matter or care. It's all the same to them. Whether this pi bond is located here or here doesn't matter to the electrons. It's still the same bonding scenario. If you look at this pi here, this pi bond is flanked by that. And if this pi bond were to shift over here, it would be flanked by identical carbon and hydrogen. Now, what's very interesting about benzene is that you get a current or a game of duck, duck, goose going around the benzene molecule. Because as one pi bond jumps over, this one gets pushed over, this one gets pushed over. I mean, you see we still have C6H6, 12 sigma bonds, and 3 pi bonds. I hope this helps. Thank you.